Hello everyone, welcome back to JDCodebase. This is the DSA Foundations Series. In the last video, we understood the time complexity, how fast our code runs as input grows. But writing fast code is not enough. Today, we are going to understand something equally important, that is the space complexity. Time complexity tell us the how much time code takes, and space complexity tell us how much memory code uses. And in the real world system, memory is the limited. So today we will deeply understand space complexity in a very simple way, beginner friendly. So let's start. Now today we will understand what is space complexity, input space versus the auxiliary space, big of 1, big of n, big of n square space, how array and variable use the memory, and how recursion uses the extra memory. By the end of this video, you will be able to analyze space complexity of any simple function, any simple JavaScript function. Now, why space complexity matter? In real world system, memory is not unlimited. Means if your code creates too many arrays or objects, your application can slow down or even crash. Backend system handle millions of users in a day and in a millisecond also. If memory usage is very high, server becomes expensive. So good code means good complexity plus good space complexity and time complexity. Now, what is the space complexity? Space complexity means how much memory an algorithm uses as input size increases. Just like time complexity, we do not measure the exact bytes, means with MB or GB. We if the input becomes double, does memory also double? Does it stay constant? Does it grow faster? And that growth is the space complexity. Now, different types of the space complexity means this is the very important point. There are two types of space. That is the first one is the input space. Second is the auxiliary space. Input space is the memory used by the input user. And like here, I have a create a let arr 1, 2, 3, 4, 5 an array. A normal array just so this array already takes memory because it stores the 5 numbers 1, 2, 3, 4, 5. If array size becomes 1000, memory also increase. But in interview, we usually do not actually count the input space. We only focus on the extra space used by that algorithm. So next one is the auxiliary space. This is the important one. Auxiliary space means extra memory used by the algorithm. That include the variables, new array, object, recursion call stack. This is what we calculate. First one is the big of 1 constant space. Constant space means the memory does not grow with the input size. Like here, I have a function sum. It's take two parameter a and b. No new array created here, no new object created here, and no new data structure like anyone. So even if the input numbers are large, memory usage does not increase. So space complexity is the big of 1 here. Means if I send here the call the sum by 1 or 2 digit numbers, it still return the sum a plus b. There is no matter of the space complexity here. But very important point here is the small number of variables is the constant space. Now next one is the big of n linear space. And in this new memory grows proportional to the input size. As the size increase of the n and the space complexity increase. So here if you see in the example, I have a function copy array. This take an array arr, and in this we create a new array, means input array has n elements in this arr, and we create a new empty array, new arr and empty array. Then we push every element into the new arr by using this for loop. So if the input size is 5, new array size becomes 5 because we are running from the I equal to 0, I smaller than arr dot length. So if input size is 1000, new array size is becomes the 1000. So extra memory grows linearly as the size increase, input size increase, the new array size is also increase. So here space complexity becomes the big of n. So this is a very common in the problems comes. Now next one is the big of n square, quadratic space. Now memory grows very fast. This is the most important. Every time we have to optimize this space complexity. So in this, let's see example here is the function create matrix. In this create matrix, if n is 3, matrix becomes 3 by 3 and 3 by 3. So that means 9 elements 1, 2, 3, 4, 5, 6, 7, 8, 9 means a matrix of 9 elements. If n is 10, matrix becomes the 10 by 10, that means the 100 elements. So memory grows n cross n, and quadratic space can be dangerous for the larger input. That's why space complexity is the big of n square. Means for a smaller input, it's is the square of that input size. Now, does a loop always use the big of n space? Here, if you see, this is a very basic question, where if I say in the interview means a tricky question. Does a loop always use the big of n space? No. Like here, this is a simple for loop. It runs from I equal to 0, I is smaller than n, and I plus plus means till the n elements. And here I am just printing this I, console.log I. So this loop runs n times, but do we create new array? No, only one variable exists, that is the I. And so even if a loop runs 1,000,000 times, memory does not increase in this for loop, and space complexity becomes the big of 1 here. And very important point here is the loop does not means the extra space. Many beginners means link with the, if we are using the loop, it's link with the extra space. No, loop does not means the extra space. Only new data structure increase the extra space, either it is a array or object we are performing here the operation. Now next one is the recursion and the call stack space. This part confuses many beginners. Does recursion uses call stack? As the recursion uses the call stack memory, we already know. A basic example is like factorial. In this, if we what is factorial? That is the 5, 4, 3, 2, 1 means every time we decrease by 1 and multiply it by previous one. So a factorial, if we call the factorial for the 5, then it factorial 5 wait for the factorial 4, then 3, then 2, then 1, and this continue until the factorial of 0. So all these function call stay in the memory, in the heap memory. So if n is equal to 5, these are, there are 5 function calls. First one is this, second one is this, third, fourth, and fifth for the 1. So that means space complexity is the big of n. So recursion always use the stack space. If n is 5, then stack is the 5, and space complexity always the big of n. Now solution for this is iteration versus recursion. Let's see the same code for this factorial, same example of the previous one, like factorial, but this time we only use this normal function. We only use the result, and here result is equal to 1, and start a for loop, and we are just multiplying the value from 1 to n. So here we only use the result and a I variable, a constant variable. No recursion, no call stack growth, so space complexity is stay 1, big of 1. Same problem but different space usage. This is why space complexity is matter. Here we are getting the space complexity big of n, here we are getting the space complexity big of 1. This is very important for the interview purpose, perspective. Now let's see quick comparison of the space complexity. Big of 1 is the best one, big of n is acceptable, but still we have to optimize this. Like here in the factorial we are getting the big of 1 here, iteration, and big of n in the recursive. And big of n square is the expensive one. As the input grows, quadratic space grows very fast in the big of n square. That's why we avoid this big of n square space complexity every time. And sometimes program crash because of high memory usage, so that's why we have to always optimize till the big of n at least. Now find the there are some questions for you. Find the space complexity for this example function. For this let me tell you here, let sum equal to 0, and if simple follow means we are getting the calculating the sum of an array. So here we are just using a simple sum variable and a I variable. So here time complexity is the big of 1. So as this is a normal one, space complexity. So you have to find this for this example 2 and example 3 and comment down the answer. Now today we learn the space complexity measures the memory growth. We focus on the auxiliary space, and variables take the big of 1. Space complexity we can take the big of 1, and new array of size and take the big of n, and matrix use the big of n square space complexity, and recursion use the call stack. So, and very important part is the loop alone does not increase the space. Now you understand both the time complexity and the space complexity, and these two together form the foundation of DSA. If you understand this clearly, every further topic like array, string, recursion, trees will become easier for you. If this video helped you understand space complexity clearly, like the video, continue the DSA Foundation series with me. In the next video, we will start applying these concepts in the real problem solving. See you in the next one. Keep learning, keep building. This is JDCodebase.